that online. Well, on this topic of land management strategies, our next speaker is Royce Larsen. Royce is um, a watershed and natural resource advisor working in the central coast of California, out of San Luis Obispo, covering the entire central coast. And he's going to talk to us about one of the most important resource values of oak woodlands, and ones that planners really pay a lot of attention to, and that's watershed management. And so I'm going to turn it over to Royce to talk about watershed management in oak woodlands. So, Royce?
Okay, thanks, Rick. I'd like to just notice it's chapter 4 in the book, if you are looking through your book at all, and pay attention to the fact that David Lewis and Jana Valakovic were also authors on that chapter, and provided a lot of information for that. First of all is, what is a watershed? And that's a question that you can answer in a lot of different ways. It can be synonymous with a drainage basin or a catchment. I actually think catchment's a better word for the fact that we want our watersheds to catch the water and not shed it. And we'll get into a little bit more of that as we go through this talk, a little bit of why that is important. It can be defined on terms of how large it is, from a very small, it could even be 1 acre or less, up to thousands of square miles, depending on what river or what stream it is you're concerned about. Probably what's most important is, if you're working in a watershed, is the jurisdiction. Who owns what land? Is it private, state, federal? And are all the players there playing as you go through watershed issues? Next question is, what is a stream? And there's a lot of different ways to answer that one, all the way from the topographic blue line that you find on maps. The stream order scheme. Is it a starting with the very small streams at the very top of the headwaters, a first order stream, then they come together and you have a second order stream? Or are you looking at the California's forest practice rules? Is it a fish-bearing stream or not? Or is it a stream that drains into a fish-bearing stream? And sometimes that may play an important part in the management and what you do. Rosgen's stream type based on the stream morphology. Is it a very steep gradient versus a meadow situation? And that's important when you start comparing how things happen on a different stream, and when you're looking at the management of it. Hydrologic method. Is a stream a perennial stream, an intermittent, or an ephemeral? Perennial being that it runs year-round. Intermittent being that it will begin in the rainy part of the season and then end sometime into the late spring or early summer. Or ephemeral, where it only runs in response to a large storm. However you decide to look at this issue of what is a stream, probably the best way is to simply go out and say, does it have a defined channel and a distinguishable bed? And if it does, it probably falls under some rule or some regulation. Most of the streams in our oak woodlands are intermittent in nature. It takes usually 6 to 10 inches of rainfall in order to get them running. Depends on what the soil is, the geology, and the water holding capacity, the timing and the intensity of the storms. So that's what we deal with mostly. The ones that are perennial usually start in higher elevations, more of our forested watersheds, and then flow through the rangelands or the oak woodlands. One of the questions that we often ask is, what is a properly functioning stream? And there's a lot of things that can go into that. Certainly the geology of it, the soils, the vegetation that's around it. But what a stream has to do is deal with the energy that it is given. And it's mostly in the form of kinetic energy. And that formula for kinetic energy is 1/2 the mass times velocity squared. The velocity is the key. As velocity is doubled, then you say you go from 1 mile per hour velocity up to 2, well, you have 4 times the energy. But when you go from 1 mile per hour velocity up to 3, then you have 9 times the energy. So it's an exponential function. And the way that streams usually develop to handle this energy is they have a floodplain. And as the waters rise, they go flood out over the banks into the floodplain so that they can dissipate that energy, drop their sediments, and then when the water recedes, it comes back down into the stream channel itself. On average, streams will flood every 1.5 years. Well, what drives these streams? Certainly it's the hydrologic cycle. The hydrologic cycle is what links land to water quality. It drives all of our nutrients, our other cycles that happen out on the landscape. So that's a very important aspect of what we do. And like this year, at least in the southern part of the state, we've had very little rainfall. Very little is happening in our streams. Further north, you may see a lot more happening this year and perhaps in other years. One of the things that we talk about is our streams, but yet they are a very small part of the watershed. What happens on the main part of the watershed, the 95, 98% of what isn't a stream or a riparian area? And as that rainfall comes and lands, it either hits something, a vegetation, and it's intercepted, or it gets into the soil and infiltrates and moves down through the soil profile. Once it's in the soil profile, it can go subsurface and come back to a stream, or go down in and recharge groundwater, and then flow back into a stream later. One of the things we'd like to think of in a watershed is that we want it to capture the water, store it for a time, and then release it safely. When it's not released safely, we get into problems such as erosion. And erosion is simply the detachment and transportation and deposition of soil, either by wind or water. In this chapter, we focus on water because that's the main idea of what we're talking about here. In erosion by water, there's a couple of things that are really important. One is the physical characteristics of the soil itself. Is it a sandy soil or a clay soil? How much organic matter is there? What is the aggregate stability? What is its ability to resist the energy that is coming to it? And then, of course, that other most important idea there is that energy of the water acting on the soil. That energy can come in forms of raindrops, which act like little explosions and dislodge soil particles, and moving them downslope by gravity. The other thing it can do, raindrops can do, especially if it is hitting bare soil, is take the soil particles and actually cause them to form a seal, which prevents infiltration, hence increasing surface runoff. You get a lot of surface runoff, you build up that energy, and lots of things begin to happen. 1 inch of rain in 1 hour, for example, can produce 1,800,000 foot-pounds of energy per acre. So that's a lot of energy that's out there hitting our watersheds. Now in oak woodlands, usually we have cover over the soil, so splash erosion or that erosion coming from raindrop is pretty minimal in most of our oak woodlands. And what we deal with the most is the other type of erosion, that of rills, which are small little channels developing and then eventually turning into gully erosion. This is one of the things that we have here in California in our oak woodlands is nationwide, most erosion occurs when the annual precipitation falls between a zone of 14 and 40 inches. And that's right where our oak woodlands are. And some people in California have said that soil in California is eroding 80 times faster than it can be formed. that creates a problem. If we want to have other things like trees grow or crops and things, we need to be careful about this concept of erosion. A couple of ideas of erosion. One is it is natural. It has happened in the past. It will continue to happen in the future. In fact, all of our farm fields are there because of erosion. There's certain things that make natural erosion. Certainly the idea of climatic or geologic situations that occur. If some of our especially coast range mountains have uplifted so rapidly that the slopes are unstable and we get sliding and sloughing. We get wildfires that come through. They can then prevent or open up the soil to erosion, and then as the water and stuff moves through down into our streams itself, we can have erosion occurring there. This whole idea of it being natural and erosion process going on has gone on, as I said, over geologic time. In more recent time, it's kind of an interesting little quote out of the Lewis and Clark expedition in a book that Stephen Ambrose wrote called Undaunted Courage, where he quoted them as saying, "The party is much afflicted with boils, and several have dysentery, which I contribute to the water, which is muddy." So the captains urged the men to dip their cups below the surface when they go for a drink of water. The surface was full of scum, mud, and debris. And if the men dipped their cups deep, they would get cleaner water. That was in 1804. How are we doing today? We still have the same kinds of issues and that going on. And they actually weighed the water with buckets, a very crude way of measuring it, and found out that the Missouri's was heavier because it carried more mud. That had to be a lot of mud to be able to make that determination by weighing a bucket of water. However, natural erosion does occur, but we also have accelerated erosion. And that is the issue that we need to be concerned with. What causes accelerated erosion? And certainly overgrazing can, our farming practices, construction, roads, all those things can contribute to that. Along with our soil being eroded 80 times faster than it is developing, there's enough soil eroded each day in the U.S. to fill a line of dump trucks 3,500 miles long. That's across the whole country. So it's a lot of erosion that is occurring, some natural, some accelerated. An example of an accelerated erosion happened, an example that I like is the Malakoff diggings up east of Sacramento in the foothills there, an old gold mine where they took a monitor and literally washed away the sides of the mountain in order to get the gold. They realized in the late 1800s, early 1900s that was not a good practice and quit doing it. However, today, the one slide right below the Malakoff diggings picture there shows a muddy stream, a stream that was running through that area, compared to a stream one drainage over during the same storm about 10 minutes apart. One coming through the Malakoff diggings being full of mud or sediment, the other one being clear. So accelerated erosion is and can be a problem. The way, and this is a complicated diagram, I apologize for that, but the point is management is what determines whether it's accelerated versus natural. And if you do good management, it seems to help, and you get this kind of upward spiral that improves our soil and our watershed functions. Whereas if you do poor management, where you open up the soil, you leave it uncovered by grading or other things, you get this downward spiral that can actually cause more problems. When we start looking, another thing that in addition to erosion, when we start looking especially at our oak woodlands and the trees, we find that an individual tree really has an impact on the fertility of the soil, and they have these little islands of fertility. there will be 3 to 5 times more litter under a tree than out in the open grassland. 2 to 3 times more organic matter. 35–40% more organic carbon and nitrogen. So if we remove these trees, not only are we going to open it up for the potential of erosion, but we also open it up for the leaching of these nutrients. And it can take as much as 10 to 15 years, if you say you completely cleared a watershed of oak trees, for it to reach a new steady state of that cycling of nutrients that goes on. A couple other issues that are not in the chapter, but are important. One has been important for a long time. Another one is, in the recent years, has gained more importance in looking at what will happen in the future. And the one issue is that of roads. A lot of information can be found out there about roads. I've given a couple of examples here on a pamphlet, Low Maintenance Roads from Wildland Solutions. That's where this diagram comes from, on how to build roads to prevent that erosion from happening. Another book is the Handbook for Forest and Ranch Roads by Bill Weaver and others. Very important concepts in there, and in those ideas of the roads and how to build them to reduce the erosion potential. Another important factor that's gaining a lot more notoriety and more information is being put out all the time is that on climate change. And 2009, our Ag and Natural Resource Vice President Barbara Allen Diaz helped summarize and work on the Intergovernmental Panel on Climate Change, and in this volume of California Agriculture kind of summed up some of the effects that we could look forward to. So there's some, along in that book as well as many others, there's a lot of information about climate change and what might happen. Just a little bit about roads. As we look at our ranches in particular, roads is where most of the sediment comes from, and how they're designed and the ideas of what you can do to help prevent that. It's that whole idea of creating these hard, bare soils that are resistant to infiltration, causing the surface runoff and the buildup of extra flow in our streams. Culverts, probably one of the biggest problems out there. Water that comes through a pipe, of course you're going to increase the energy, and then you have to deal with what happens as it comes out the end of that pipe. The whole idea of getting the proper size of a culvert in so that you do not increase that velocity is very important. And one thing to think about is, for example, if you need a 72-inch culvert, 3 24-inch culverts does not equal one 72-inch culvert. That's also important if you're talking about fish passage or something in certain streams. You need to be very careful about that. Climate change. As we look at the way these streams function, and if you have, like the State A there, proper functioning stream, it has a flood zone to it, but as they begin to downcut, it traps the water, builds the energy. Those streams are going to downcut until they can't go any further. Then they start cutting the banks out until they build themselves a new floodplain to handle the energy that's in the stream. With climate change, the predictions are the droughts will be worse and the wet years will be wetter, or the floods. So that means the drier years, it's going to be harder on the vegetation along the streams. The wetter years, we're going to have the increased stream flow and higher energy. It could become a very interesting issue. Just real briefly, a couple of things on the water quality laws and the regulations. A lot of different laws out there going on that you have to think about when you do management. From the federal level with the EPA and NOAA and National Marine Fisheries Service, U.S. Fish and Wildlife, and Army Corps. We start dealing on state laws with the State Water Resources Control Board, all of our different regional boards, Fish and Game, Coastal Commission, and others. There's also local laws dealing with grading and pesticides and groundwater and wells and etc. Even though sediment is a very important issue, that what we're finding the most right now on the Central Coast, though, is fecal indicator bacteria and not sediment so much. So it just depends on who you're working with and what the issues are. And finally, to kind of wrap it up and end, since boundaries in watersheds go across different jurisdictions and ownerships, it's very important to work in a watershed group if you really want to solve the problems that exist out there, so that everyone is on board that's upstream from you or downstream from you to help solve the problems. That's all I got, unless...
Okay, thanks, Royce. We did get one question in, but I think we'll hold that till the end there. It does pertain directly to this, Royce, but we'll get to that in just a moment here. So, thanks very much, Royce.